The last few lessons we've been talking about scatter plots and lines of best fit, distance time graphs, recognizing linear relationships using first differences, and now we're going to talk about something called rate of change. So we're going to talk about what that is and what it's used for in the context of linear relations. So I'll start with this example. I have a graph here. My independent variable is time, my dependent variable is distance, and I have 3 different people. I have Bob, Bill, and Brian. So the question is, who walked the fastest? Well, what do you think? Fastest means you go a greater distance in a shorter amount of time. So the fastest person would correspond to the steepest line. So if you look carefully at the graph, you'll find that Bob has the steepest line on the graph. So that's how we can get our answer. Bob walked the fastest. We know this because he had the steepest line on the graph. Now the next part. Calculate their speeds to back up your claim. Okay, so now we can't just look at the lines and see which one looks the steepest. We actually have to do a calculation. So I'll start with Bob. If I look at where Bob started and where he ended, I can look at the distance he traveled and the amount of time it took. So I can see from here to here, Bob walked 12 meters and it took him 4 seconds. So 12 meters in 4 seconds, I can get my speed, meters divided by seconds, I get 3 meters per second. I look at Bill, he traveled 8 meters in 8 seconds. So when I calculate his speed, meters divided by seconds, it's 1 meter per second. Brian traveled 6 meters in 3 seconds. So when I take meters and divide by seconds, I get 2 meters per second. So I looked at just visually who had the steepest line. That was Bob. And I also calculated the speeds using the change in distance over the change in time. And I can back up my claim. I can see here that Bob has the fastest speed. And this brings us to the whole idea of this lesson, the rate of change. So speed, which we just calculated, is just one example of rate of change. So this rate of change is, well, it's a rate, which we talked about in a previous topic about, it's a comparison of different units. So in the case of speed, the units we're comparing are meters and seconds. So the rate is meters per second. And it's a rate of change. So we're looking at how the distance changes as the time changes. So when you have a graph, you can calculate the rate of change. And this is the calculation right here. To calculate rate of change, you take the rise and divide by the run. So let's talk about what rise and run mean. Well, when we have a graph, we have a y-axis and an x-axis. So when I refer to rise, that's the change in the y values. Rise means up and down. The run means left and right. So it's the change in the x values. So in the previous example, we were calculating speed. So speed was our rate of change. And to calculate that, we figured out the distance, the change in the distance, divided by the change in the time. And that's how we calculated speed. So it doesn't matter what values you are graphing on your y-axis or your x-axis. You can calculate the rate of change by taking the change in your y values divided by the change in your x values. So you'll often see a shorthand of this equation written like this that I have in blue. So instead of writing out rate of change, you'll see the acronym ROC, stands for rate of change. And instead of writing rise over run, you might see this is a delta y over delta x. Delta is the Greek letter that looks like a triangle. And that letter in math always refers to a change in some value. So delta y means the change in your y values. And that's exactly what the rise is. Delta x means the change in your x values. And that's what run is. So this is a very important equation to remember. You need to know how to calculate rate of change for a graph. But it's best to illustrate with an example. So here I have a graph of Ferd's walk home. So I have his distance from home in kilometers on the y-axis, and I have the time it took him in minutes on the x-axis. So here I have my independent variable, time, and my dependent variable, distance from home. So if I'm to calculate the rate of change for this graph, I need to remember the rate of change is equal to the rise over the run. So the change in y over the change in x. So to figure that out, I just have to find 2 points on the line. Well, here I have 4 points given to me that are on this line. I just have to choose 2 of them. So really, just pick your favorite 2 points. I'm going to choose these 2 points. But you could choose this point, you could also choose this point, any combination, as long as you choose 2 points. And then what we do is we figure, okay, what's the change in y? Well, from one point to the other, I'm starting with a y value of 3, and I'm ending with a y value of 1. So you can see that in the coordinates also, starting at 3, changing to 1. So if I'm starting at 3 and I'm going down to 1, what's the change? Well, I'm going down 2 units. And if I look at my run, or my change in x, well, I'm going from 20 to 60. So I'm increasing by 40 units. Okay, so let's go back to our formula here for rate of change. My rise was -2 kilometers, and my run was 40 minutes. So I have rise over run, and now I can just do this calculation. -2 divided by 40. I get a negative value, -0.05, and the units for my rate of change are just the units for my rise with the units for my run. So it's kilometers per minute. Kilometers per minute. So what this means is if it's negative, it just means his distance is getting smaller over time. It looks like a decreasing line on the graph. We also know, since this is kilometers per minute, this is a speed. So this rate of change is his speed. He's walking 0.05 kilometers per minute towards home. This next graph over here, we would expect that this rate of change is positive because his distance is increasing over time. To calculate this rate of change, we're going to do it the same way. We're going to find 2 points on the line, and then we're going to find the rise and the run between them. This line doesn't have points given like this one did. So really, all you have to do is find points that you know for sure are on the line. So we talk about the line has to be going through the crosshairs. So like here, there's the crosshairs. Or this point here, the line goes through the crosshairs. I know for sure it's on that point. I wouldn't choose a point here, for example, because I don't know what the y value is or what the x value is. I'd have to estimate. So we want to know for sure. So why don't you pause the video and try this one on your own. Try to find the rate of change. So with this one, rate of change is rise over run. So the rise, he's going up 150 kilometers in 3 hours. which ends up being 50 kilometers per hour. So I don't know about this, but he's walking really fast. And it doesn't really matter which points you choose on the line. I chose this point and this point, but you could have chosen this point and this point, or this point and this point. It doesn't matter. You'll end up with the same rate of change, or at least you should. In this next example, we're going to compare Bob with Roberta. So Bob starts at home and walks 400 meters every 5 minutes towards school. Roberta is at school 4 kilometers away. She walks towards Bob's house at a speed of 100 meters per minute. So for each of these people, I want to make a table of values. Time is my independent variable. Distance from Bob's house is my dependent variable. And I'm going to figure out what the distance is every 5 minutes. Okay? So let's start with Bob. He starts at home. So if he's starting, what's his distance from his house? Well, he's at home, so his distance from his home is 0. But he's walking 400 meters every 5 minutes. So 5 minutes later, what's his distance from home? Well, he's walking 400 meters every 5 minutes. So every 5 minutes, we're going to add 400 meters to his distance. So this should be your table of values for Bob. Okay, let's go back over to Roberta. So Roberta is at school 4 kilometers away. So when time starts, how far away is she from Bob's house? Well, she's 4 kilometers away, but this table of values has meters as the units. So you're just going to have to remember there's 1,000 meters in 1 kilometer. So if there's 4 kilometers, that's 4,000 meters. She walks towards Bob's house at a speed of 100 meters per minute. So every minute, she's 100 meters closer to Bob's house. So if she's traveling 100 meters each minute, how many meters would she travel in 5 minutes? Well, that'd be 500 meters. So 5 minutes later, she's going to be 500 meters closer to Bob's house. So her distance will be 3,500 meters. Okay, so every 5 minutes, she's 500 meters closer to Bob's house. So you can update the table of values. Okay, so for each person, we've developed a table of values comparing their time with their distance. And now we can calculate their rate of change. So we're going to use our formula for rate of change. It's the rise over the run, or change in y over change in x. In our table of values, x is on the left, y is on the right. Independent variable, dependent variable. So for Bob, his distance changes 400 meters every 5 minutes. So that's rise over run. Change in y is 400 meters. Change in x is 5 meters. And now I can just do my calculation. 400 divided by 5, that's 80 meters per minute. So Bob is walking at a speed of 80 meters per minute. That's his rate of change. Pause the video and try to calculate the rate of change for Roberta. If you follow the same steps, you should end up with 100 meters per minute. Now, it should be negative because her distance is decreasing over time. Okay, the last thing I want to do in this example is to come up with an equation for d, the distance. So I'm going to use the variables d to represent distance in meters and t to represent time in minutes. If I look at Bob, he's traveling 80 meters per minute. His starting distance is 0. So if I want to calculate his distance at any point in time, all I have to know is how fast he's going, and how many minutes he's been walking. So if he's been walking for 1 minute, that means his distance will be 80 meters. If he's been walking for 2 minutes, that means his distance would be 2 times 80 meters or 160 meters, etc. So to calculate Bob's distance from his home, all we have to do is take his speed or his rate of change and multiply it by the number of minutes, the time. Roberta, on the other hand, well, yeah, she's traveling 100 meters every minute towards Bob's house, but she's starting 4,000 meters away. So to calculate her distance at any point in time, we know it's going to start at 4,000 and it's going to decrease by 100 meters every minute. So that would be how I would write that. Her distance starts at 4,000 meters and it decreases by 100 meters every minute. 4,000 minus 100t. So I can calculate Roberta's distance from Bob's house for any number of minutes. So let's say I wanted to extrapolate to 30 minutes. Well, I could plug in the number 30 here. 30 times 100. Subtract that from 4,000 and I would get the distance from Bob's house. For this next example, I'd like you to take a look at the graph and calculate the rate of change. Pause the video and see how you do. So if you pick 2 points, do the rise, do the run, you end up with 2 centimeters per hour. So things you want to pay attention to are the scale. So here, you're not counting the number of squares, so you wouldn't say the rise over run is 2 over 6. You have to pay attention to the scale. The scale is in centimeters, so how many centimeters are you going up? Well, you're starting at 4, you're ending at 8. That's increasing by 4 centimeters. Same with for the time. You're starting at 1 hour, you're ending at 3 hours, so that's a change of 2 hours. So don't necessarily just count the squares, you want to count the units on the grid. The other thing you want to pay attention to is units in your rate of change. So here my rise is in centimeters, my run is in hours, so my rate of change should be in centimeters per hour. Okay, but what does this rate of change represent? So the rate of change is 2 centimeters per hour. What does that mean? Well, for this, you have to look at the context. So here we're given a title, Stratford Snowfall. So we can assume that this is measuring the amount of snow falling over a certain amount of time. So the rate of change represents how much snow is falling per hour. And now we come to an equation. So in the previous example, we calculated an equation for the distance away from Bob's house. Now we're going to find an equation to represent this amount of snowfall. So 2 pieces of information. The first piece is we need to know the rate of change, which we already do. The second piece of information we need to know is the starting amount. So this is where the graph starts. So what's the starting amount of snow? 2 centimeters. So we're starting at 2 centimeters and we're increasing by 2 centimeters each hour. So this is my equation, and I'm using the variables a and t. As soon as I use variables, I have to say what they mean. I have to define my variables, and so that's what I've done over here. This next example is just like the one before. This time we're looking at novel reading. So we have pages remaining, the number of days. I'm going to challenge you to pause the video and try this entire question on your own, and then you can check how you did. So I picked 2 points on the line, calculated my rate of change. I noticed that the number of pages decreases over the number of days, so that's a negative rate of change. And it's changing by 15 pages each day. So my rate of change is negative 15 pages per day. So what that means is they have 15 fewer pages to read each day. So they're starting at 90 pages remaining, and that decreases by 15 pages each day. So I can have my equation, the number of pages remaining is equal to 90 minus 15 times the number of days. And I've defined my variables. For this last example, we're talking about Brenda. So Brenda has $6 in her piggy bank. Every 4 days, she adds $1.50. So what I would like you to try to do on your own, and then I'll show you all my work here so you can check, is to create a table of values, create a graph, determine the rate of change, write an equation, and then answer the question, how long until Brenda has $100? See how much of that you can do, and I'll show my solutions and you can check as you go. So to make my table of values, I knew that she started with $6 in her piggy bank. So on day 0, she has $6. Every 4 days, she adds $1.50. So I just went every 4 days and added $1.50 each time. So you can see I've just indicated that here. Every 4 days, adding $1.50 each time. To make my graph, I just took my points that I figured out on my table of values and I plotted them on the grid. Then I drew a nice straight line through my points. Next, I'm going to calculate the rate of change. So find 2 points on your graph, calculate the rise and the run. So when you do that, you end up with this crazy number. Basically, it's 37.5 cents per day. Now, I want you to notice this other thing too. If I look at my first differences compared to the increase in my number of days, well, that looks like my rise and my run. And that's true. So you can calculate rise and run using your table of values as well. For the equation, remember I'm starting at $6. It's increasing by $0.375 per day. So then I can make my equation for that. I'm using M to represent the amount of money in dollars and D to represent the number of days. So the amount of money starts at $6 and then we're adding $0.375 each day. So that would be my equation. Now I can answer this last question. How long until Brenda has $100? So you could make a graph where you extend the number of days to 100, or you could make a table of values and add the number of days until you get to 100. And those would work. They'll be very time consuming though. The most efficient way of solving that problem would be to use your equation. So if you want to know how long until Brenda has $100, well, you know the amount of money is $100, so you know the value of M. And then you can use your algebra skills from previously to solve for D. So I'll show my work over here. So this is just my equation that I made. Now I know M, the amount of money, is $100. So I substitute 100 in for M. Now I have an equation that I can solve. So I just collect my like terms and simplify. But now I have 94 equals 0.375D. I need to solve for D. So remember, right now it's being multiplied by 0.375. So to isolate D, I need to do the opposite operation. I need to divide by 0.375. And if I do that on both sides, now this and this cancel out. So on the right-hand side, I'll just be left with D, and then I just do the division on the left-hand side to see what I get. And I get an answer of about 251. So since D represents the number of days, I'm just going to round it to a whole number. So now I can actually answer the question. It will take her 251 days to get $100. Okay, so for this entire lesson, the things you want to know how to do are calculate the rate of change, and then use the rate of change to solve problems. And you might have to make an equation in order to do that effectively. Here's your independent practice to try. So try all these, see how it goes. If you get stuck, please let me know, and I'll do my best to help.